Okay, I hope you're good to go here with the next topic in NMR because it's going to start to get a little bit hairy. So spin-spin splitting is also known as coupling, and it is what is behind all those interesting patterns we see in NMR. So if the effective magnetic field is what it's all about, and that's really what it is all about in NMR, what magnetic field does that little nucleus really feel? That's what gives rise to the chemical shift. So if the effective magnetic field is the be-all, end-all, then what's the story with a molecule like this? We should identify that obviously we have two sets of homotopic nuclei, so we would expect two separate signals. And up until this point, the only thing we've concerned ourselves with is what the chemical shift might be. And looking at the electronic environment of these two hydrogens, this red hydrogen being attached to a carbon with two chlorines, two electronegative chlorines, would be considerably more de-shielded than the blue hydrogens. So this guy would be de-shielded and downfield compared to the blue hydrogens, which only have the one chlorine. However, now we're going to look at the patterns that arise from the fact that this hydrogen here, the little red hydrogen, is basically a spinning magnet, right? It's a spinning nucleus, NMR active. It generates its own magnetic moment. And of course, similarly, right next door to the red hydrogen are two little spinning magnets. So these neighboring magnets are definitely going to affect the magnetic field that each hydrogen feels. So let's look at this in some detail. With a little magnet spinning right next door, well, first of all, we've got the magnet, the external magnet. That's really should be EXT there. So we've got the magnetic field that's due to the big old magnetic field of the instrument. But in addition, paying attention now to the blue hydrogens, right next door, my red hydrogen could either be in the alpha state aligned with the external magnetic field, or the beta state pointing against the magnetic field. So, as a result, the blue hydrogens feel an effective magnetic field that is a little bit stronger because of the alpha state of the red hydrogen, and a little bit weaker because of the fact that the red hydrogen right next door is buffeting against the external magnetic field. So what do we see? We see this doublet for the blue hydrogens, where the reinforcement of the external magnetic field by the alpha state pulls the signal for the blue hydrogens downfield just a hair, and the counteracting of the beta state reduces the effective magnetic field, making for a smaller delta E spin, and as a result, slightly upfield. So the actual chemical shift for the blue hydrogen is right smack dab in the middle of this pattern, which we would call a doublet. Well, what would the red hydrogen show up as? This is described in the n+1 rule. So basically, n is the number of neighboring chemical shift equivalent hydrogens, neighboring homotopic hydrogens. Well, there's two. So the red hydrogen should show up as a 3-line signal, aka a triplet. And the actual shapes of these doublets, triplets, quartets, etc., are described by Pascal's triangle, where the outer edges of the triangle are ones, and you add up the two numbers just above. So a singlet obviously has an intensity of 1. A doublet, the lines are equal in intensity. A triplet, the intensity is 1 to 2 to 1. A quartet, 1 to 3 to 3 to 1, and so on. So the n+1 is a really, really powerful predictive tool, and it really helps us identify carbon structure. So let's look at another quick example here. This one's almost exactly the same. Now instead of a 1,1,2 trichloroethane, we have 1,1 dichloroethane. And again, obviously, two sets of homotopic hydrogens. So first let's predict what the chemical shift should be. Well, we've already decided that with a hydrogen attached to a carbon with two chlorines, this red H sub B is going to be pretty far downfield. So who knows? I'm going to guess around 6 parts per million. There are books that we can use to look this up, but it's going to be pretty far downfield. Whereas this is a sort of kind of almost normal methyl group, but it's next door to that pretty de-shielded carbon, so I'm going to say this maybe is around 1.5 parts per million. So we know we should see a signal worth 3 hydrogens in terms of its integral value, around 1.5 parts per million, and we should see a signal maybe around 6 parts per million worth 1 hydrogen. But what's the pattern going to be? Well, according to the n+1 rule, this red hydrogen is next door to 3 blue hydrogens, so that should be a quartet. And again, the blues are next to just 1 homotopic hydrogen, so that would again be a doublet. Let's see if we're right. Well, of course we're right, or else I wouldn't have chosen this example, right? Well, but anyhow, what I'm trying to tell you here in this little cutout of the actual proton NMR spectrum is that the gap between the two peaks adjacent right here, that gap is revealing of kind of the strength of the interaction between the adjacent nuclei. It's called the coupling constant, and as this diagram shows, the gap between each of these 3 peaks, they're all going to be the same. So in theory, this distance is equivalent to this distance, which is equivalent to this distance. And because A and B are coupled, the coupling constant for JAB here is the same thing as the coupling constant for JAB here. And it is absolutely no significance that they say BA here and AB here. That's completely arbitrary. So what this is basically telling you is hydrogens that are coupled have the same coupling constant. And that's pretty handy when you're trying to determine structure and trying to figure out who is coupled to who. They have to have the exact same coupling constant. Alright, coupling constants can be extremely diagnostic, so what we're talking about in these previous 2 examples is kind of regular, normal, right next door, neighboring coupling. This is the n+1 type coupling. Vicinal coupling, that's what this is called. So we're looking at next door neighbors here, and the size of that gap is really quite reliably just right about 7 hertz. Now, so this is the one we'll focus on most of the time. Lots of things that are pretty valuable to look at on this chart, though, which I will say is taken from another textbook, but in your textbook it's table 16.1. All right, so first thing to point out, typically speaking, unless you're neighboring, there's no coupling, there's no splitting. So H sub A and H sub B, assuming there's no hydrogens on this middle carbon, they will not split each other. They don't have any impact on each other. Usually, hydrogens that are on the same carbon, like these two, typically, these two are absolutely the same. Typically, they're homotopic. So you may be wondering, well, how can I have a carbon where the two hydrogens are on the same carbon, but they aren't homotopic? We'll get to that. That's where stereochemistry rears its ugly head. But here's an example. When we start throwing pi systems into the mix, we get some interesting effects. So let's say there's a phenyl group here. Well, if there's a phenyl group here and a chlorine here, A and B are in two completely different electronic environments. So H sub A and H sub B are not homotopic, and they can couple with a really tiny coupling constant. You'll just barely be able to see a teeny split in your NMR spectrum. This kind of coupling in alkenes can be very diagnostic because, as you can see, when you have a transalkene, the coupling constant is huge, whereas a cis-alkene, it's noticeably smaller, and this is very diagnostic for determining whether or not you have an E or Z alkene. And the only thing I want to point out about these examples is that when you have a pi system, you can have coupling that goes well beyond next door neighbors. Typically, we're talking 0 to 2 hertz, pretty small coupling constants, but be aware that in certain aromatic systems, for example, there can be coupling as far away as the para and meta positions. That's long-range coupling, and we'll look at some of those more complicated examples a little bit later. So, coupling constants, valuable piece of data.